Okay, I'm going to take you through pretty much all the derivative rules. I'm going to start the video by looking at the chain rule, and I'm going to use the chain rule in all of these individual rules. If you haven't learned the chain rule yet, you might want to flip to the chain rule video and watch that, or look it up in a textbook, because I'm going to use it on all those things. I think it's a little weird that we teach all of these rules and then we learn the chain rule. I would suggest kind of mastering the chain rule or looking at the chain rule first, and then just go ahead and applying it when you learn all these rules instead of having to relearn the rules once you've mastered the chain rule. The chain rule talks about composite functions, and so you can look at the fact that we want to find the derivative of y with respect to x, and we have to do this manipulation. We have to take dy du times du dx. Now that might sound a little weird at first, but this is just the big idea and then multiplying by the derivative of the inside. So it's like the big function and then the little function, or the outside function and then the inside function. Another way to say is that if you have y and it's some function f, and then f is some function with g and sine, then the derivative of dy dx is going to be f prime of g times g prime of x. So what that's saying is take the derivative of the big function and don't change the input times the derivative of the inside. And again, when I do all these, I'll explain this. But again, I would, there's a whole video dedicated to the chain rule if you want to look back on it. Okay, so let's look at power rule. Power rule is going to define any type of polynomial, square root function, things of that nature. So the power rule says this: bring the power down, decrease the power by 1, multiply by the derivative inside. And so I guess in the video I probably should have changed that to a u, but what we're looking at is any sort of function that is 4x cubed plus 2x plus, I don't know, 3 square root of x minus 10 over x squared. Anything like this. It doesn't even have to be just a polynomial. And then we can look at the derivative. Okay, and so the derivative, y prime, or dy dx, bring the power down, decrease the power by 1. Bring the power down, the power there is a 1, decrease the power by 1, 2. Bring the power down, which is a half, decrease the power by 1. Now decreasing the power from a half to a negative a half is really just putting the square root in the denominator. Bring the power down. Now this power is negative 2. Bringing the negative 2 down is going to change that to a positive 20. Decreasing the power by 1 makes that x cubed. Again, you got to really think about what we're looking at there. The power here is negative 2. Bringing it down, it's going to change the sign, and then decreasing. Okay, so that's the power when it can be applied to all of those things. Rational expressions, square roots, cube roots, 7/4 power, x to the first power, and again, it does also predict that the derivative of a constant is 0. And again, in this case, there's no really u prime. All of these were just x's. And again, you're going to get to more complicated things down here. Okay, so what if we have a logarithm? What is just the derivative of the natural log of x? Well, the derivative of the natural log of x, y prime, is just going to be 1 over x. But how often do we just have the derivative of that? Sometimes it's going to be the natural log of, let's say, x squared plus 1. That's our y. Well, now we have to apply the chain rule. The derivative is going to be u prime over u, or some people like to say it's 1 over u, meaning the argument, times u prime times 2x, which you could then write as 2x over x squared plus 1. And again, go back up here. This is exactly what the chain rule talks about. If you have a composite function, f and then g, and again, this is f and then this is g, they're two separate functions. If you want to take the derivative of f of g of x, you take the derivative of f prime, so we take the logarithm derivative, 1 over u, and then multiply by g prime. G prime is this thing right here. And again, in all of these things, we're always going to have a u prime, a u prime, a u prime. We're always multiplying by the derivative of some inside function. So that's the derivative. Now, this is silly to think about this as a separate rule. This is just log base b. This is just log base e. And you think about if the base is in e, then that just becomes 1, and then these two rules are identical. And that's going to be the same thing down here. So if it was a log, what if it was log base 4 of x cubed plus 4x? Okay, and we want to take the derivative. Y prime is going to be u prime, which is going to be 3x squared plus 4 all over u, x cubed plus 4x. And then also in the denominator, we're going to have the natural log of 4. And again, it's 1 over u, natural log of the base, times u prime. And I just put the u prime on top because I just think it's simpler to think about it in that way. And that's how you take the derivative of logarithms. And again, these are the same rules. This just says the natural log of b, and it doesn't show up here because that's what the base of the natural log is. Okay, exponentials. Take the derivative of an exponential. So an exponential is going to look like e to the, 4x. So to take the derivative, y prime equals e to the 4x times 4. The derivative of e to the u is e to the u times u prime. So the derivative of e to the u is e to the u times u prime. The derivative of 4x is just 4. And then you're done. And it really can't get any more complicated than that. It's just, if this is a composite, if this is a function, you just multiply by its derivative. Now if it's a to the u, it's still not too big an adjustment. What if this was, 8 to the x squared? Something like that. Well, then the derivative, just follow the rule. The derivative of an exponential is a to the u times u prime times the natural log of the base. In this case, the base is 8. Okay? A to the u, and I guess they switched those, but hopefully we're okay that that order's changed. And that's how you take the derivative of exponentials. Again, the definition of an exponential is some constant to some function. If the constant happens to be the constant e, then we don't really need this natural log in there. Okay? So those are those first kind of rules. Again, we are using chain rule on all of these things. Okay? Now we're going to use product rule. Okay? Product rule is how we take the derivative of a function times a function. Much, much different than chain rule, right? So let's say we just have two functions, x squared plus 1 o times e to the x cubed. We'll use the fact that we already know how to take derivatives of an exponential. And this is what it says. The derivative of u times v, the derivative of u times v is u times the derivative of v plus v times the derivative of u, meaning the first function times this derivative plus this times this derivative. Okay, so let's look at this. So y prime is going to equal the first function times the derivative of the second function. The derivative of e to the u is e to the u times u prime, okay, plus the second function times the derivative of the first function. Okay, and what you can match up here is what I did. This is u times v prime plus v times u prime. And now we have the derivative of a product. Quotient rule is the same thing. It just involves when you take the derivative of a quotient, we'll use those exact same functions. So let's say I had e to the 2x, we'll just use another exponential, and then we'll use a polynomial. How about x cubed plus 4x? Okay, so we want to take the derivative. Y prime is going to equal v, so it's the denominator, times the derivative of the numerator. The derivative of e to the 2x is e to the 2x times 2 minus the numerator times the derivative of the denominator. The derivative of x cubed plus 4x is 3x squared plus 4 all over v squared. Remember, this is v, x cubed plus 4x, and that is usually really messy, and sometimes that simplifies and sometimes it doesn't. I mean, you could factor out an e to the 2x or something, but honestly, you're going to typically use it to evaluate. The purpose of this particular video is just to kind of go through and show you the quotient rule. Again, the quotient rule is for when you have the derivative of two functions that are a fraction. So this is e to the 2x, this is my u, and this is my v. So I have v u prime minus u v prime all over v squared. And that's how you take the derivative of a quotient. All of these rules are super similar. They're just telling you how to take the derivative of a trig function. Okay, so how do you take the derivative of a sine function? So what if it's the sine of 4x? Well, it says the derivative of sine is cosine. So then y prime is going to equal cosine of 4x times 4. And again, I'm using the chain rule on every single one of these things. I'm taking the derivative of the big function, sine, which is cosine. The argument stays the same, and then I have to multiply by the derivative of the inside times 4. Okay? What if this was y equals cosine of e to the 2x? The derivative of cosine is negative sine. So y prime is going to be negative sine of e to the 2x times the derivative of the inside. Well, the derivative of e to the 2x is e to the 2x times 2. Remember, the derivative of an exponential is e to the u times u prime. So then that's the derivative of this composite function. And again, we can keep going down the list for as many as you want. We could take tangent of the logarithm of x. Okay, so then y prime, the derivative of tangent is secant squared. Again, that's the big rule, the derivative of tangent. And so we're going to get secant squared of the natural log of x times u prime. In this case, that's my u. And the derivative of the natural log of x is 1 over x. And again, all of these are the exact same things. You're always going to have chain rule implications. You're always going to have to multiply by the derivative of the inside. If the inside of a trig function is its own function. Now, if it's just, if it's really like basic and it's just, sine x, it's just an x there, well then y prime is easy. It is just cosine x because the derivative of x is just 1 and multiplying by 1 is kind of just silly. So no big deal at all. If it's just nice and easy, you can just drop the u prime if it's just an x. But if there's a u prime, on every single one of those, you're going to have multiply u prime, multiply by u prime, multiply by u prime. And so anytime you have those composite functions, you just build off each other. Okay, I'm going to save the next video for challenge problems. So if you want to see maybe a quotient rule and a product rule at the same time, if you want to see the triple product rule, what if you have a function times a function times a function? What if you want to see a power rule and a trig function at the same time? We'll take a look at those in another video, but hopefully this gave you the basics. Again, if you look back on what we did, these are the main rules here, okay? We start out using the chain rule because I wanted to talk about it to apply to all these rules. But power rule governs polynomials, square roots, and kind of rational expressions. We have logarithm rules and exponential rules. And I want to point out that the natural log and the regular log, they're essentially the same rule. Just like e to the u and a to the u, they're the same rule. They just differ by that natural log factor. What happens if we have two functions multiplied by each other, divided by each other, and then all the trig functions? You can go ahead and look up the inverse trig rules. They're just rules you're going to have to memorize. They're not really hard to apply. They're just rules here, and then of course you get multiplied by u prime. But hopefully this gives you a basic idea on how to take the derivatives of most of the common functions that you're going to see.